Forcing pressurized gas into human lungs creates an immediate physical conflict. In mechanical ventilation, you are balancing raw pneumatic force against the highly fragile, variable compliance of biological tissue. A critical care ventilator cannot be treated as a simple mechanical bellows. Human lungs respond to pressure differently breath by breath, requiring a device that adapts instantly to avoid causing catastrophic trauma. The Dräger Savina 300 Classic resolves this tension. Rather than acting as a static pump, it is designed as a highly sensitive, closed-loop life support architecture. Looking at the complete unit, the physical hardware is entirely self-contained. It rests on a sturdy trolley base, rising vertically to a central interface. Understanding how this machine operates requires deconstructing its anatomy into 3 distinct hardware zones: the command interface, the pneumatic block, and the patient interface. Viewing the ventilator as an integrated ecosystem, rather than a collection of parts, is the first required step toward clinical mastery and patient safety. The entire physical process of mechanical breathing is compartmentalized within these 3 zones. At the top is the first zone, the digital monitoring interface. Moving down the chassis, we reach the second zone, the pneumatic block with its central ports. Finally, extending outward, we have the third zone, the physical patient interface. The overarching goal of this architecture is continuous translation. The system must turn digital clinical intent into physical pneumatic delivery, and then feed biological responses back into digital data. Let's isolate the top module, the system's digital brain. Looking closely at this screen, you find the sole entry point for setting exact clinical parameters, dictating values like positive end expiratory pressure and tidal volume. The interface also serves a second critical purpose, providing continuous, real-time sensor feedback regarding the patient's respiratory mechanics. These scrolling traces are scalars. They take invisible pneumatic forces and translate them into a visible language for the clinician. Looking at this animated pressure time waveform, we can track a single breath cycle. The trace rises from a baseline to a peak during inspiration, and the exact morphology of this curve instantly reveals changes in airway resistance. Continuous monitoring at this level is a non-negotiable safety net. It is the only way to quickly detect patient ventilator asynchrony or a sudden airway obstruction. Processing all of these physical inputs in mere milliseconds requires immense computational speed, running quietly behind the display. Ultimately, the command interface is where clinical strategy takes form as precise machine instruction. That instruction immediately travels downward from the screen into the physical hardware. This midsection chassis is the pneumatic block. This is where digital algorithms are converted into pressurized airflow. On the right side of this central panel, we locate the inspiratory limb port. This port drives the precise, pressurized mixture of air and oxygen out of the machine and toward the patient. On the opposite side sits the expiratory limb port. This port manages the return flow of waste gas. It utilizes highly sensitive internal valves to strictly control exhalation resistance and maintain necessary pressure in the lungs. This schematic cross-section shows the mechanics hidden behind the panel. High-speed turbines and gas blenders rapidly mixing distinct gas streams, pushing them through valves to hit exact pressure targets. The pneumatic block serves as the system's muscle, executing the digital brain's instructions with calculated mechanical force. Leaving the central chassis, we follow the external physical pathway connecting the machine to the patient. This metal articulated arm extending from the side is a critical safety feature designed specifically for strain relief. Without adequate strain relief, the sheer physical weight of the delivery hoses pulling down on a patient's airway can cause accidental extubation. Supported by the arm, the delivery hoses utilize a dual limb configuration. This strictly separates fresh gas traveling to the patient from waste gas returning to the machine, preventing carbon dioxide rebreathing. At the very end sits a blue test lung. The engineering purpose of this bag is to simulate the physical resistance and compliance of actual human lungs. Interacting with this simulated compliance allows the machine to run rigorous pneumatic self-tests before it is attached to a human being. The patient interface is the exact point where mechanical gas delivery meets biological reality. While we have deconstructed the machine into distinct zones, it only functions as a unified, continuous loop. Looking at this complete view of the system, we can trace the forward journey. Digital commands trigger the pneumatic block, pushing airflow out the inspiratory port and down the hose. The delivered gas meets the physical resistance of the lung, expands it, and begins the return journey up the secondary hose into the expiratory port. On this final leg, highly sensitive sensors at the ports measure the volume and pressure of the returning gas, translating the physics directly back into digital data on the screen. The machine executes this entire cycle in milliseconds, continuously adjusting its delivery to match microscopic changes in lung mechanics instantly. This real-time, closed-loop feedback is exactly what makes the device a highly responsive life support system. Mechanical ventilation remains a high-risk intervention performed on extremely fragile human tissue. Deep familiarization with the hardware configuration is a direct requirement for maximizing patient safety and minimizing harm. As seen in this complete view of the Savina 300 Classic, the entire architecture relies on perfect synchronization. Clinical mastery requires understanding exactly how digital pixels on a screen, internal pneumatic forces, and physical breathing circuits all function as one.